Greetings everybody, and today we're going to be taking a look at something a little bit different. We're going to be taking a look at the Bromwich contour, which is used in order to compute the inverse Laplace transform. So for the Laplace transform, if we have some function of t and then we take the Laplace transform of this thing, we have a nice integral formula that we use. It's the integral from 0 to infinity of f of t times e to the minus st dt, and that gives us some function capital F in terms of our Laplace variable s. And the question is there a formula to go backwards from this? So can we plug our capital F of s into some formula and get back our original f of t? And the answer is yes. It's not a particularly nice formula, but here it is over here. If we have our function capital F of s, and we take the inverse Laplace transform, that we can compute that by taking 1 over 2 pi I and then evaluating this integral. And the integrand over here is pretty similar to the original Laplace transform formula. So where does the Bromwich contour come into play? Well, if you take a look at this interval that we're integrating across, we're going from gamma minus infinity to gamma plus I infinity. So in the complex plane, all this is just some kind of line, vertical line like so, with a real part, let's say our variable is s, to be equal to gamma. And gamma, we want it to be big enough such that everything to the left, it's able to enclose all the poles of our function over here. So usually our function does have poles, and we require that gamma is big enough such that it's to the right of every single pole. So how do we compute such an integral? Well, since it's in the complex plane, it would be nice if we can use the residue theorem for that, but in order to use the residue theorem, we need some kinds of contour to integrate around. So that's why in this picture over here, we've basically considered a finite case of our interval of integration. So it still has a real part of gamma, but it doesn't quite extend from minus infinity to positive infinity. And what we do instead over here is we cut it off at these endpoints, and we just construct some kind of circle that goes around it with a radius of r. And remember, as I said before, all the poles of the integrands lie on the left of this gamma over here, which means that our contour is sufficiently large enough to enclose all of those poles, well, at least in the limit as our r approaches infinity. So what is the point of this video? I guess it's just to improve a lemma that I find is pretty important. It's that when you take the limit as r approaches infinity on the integral over gamma, which is this big circle over here, in fact the integral goes to 0. And why is this important? Well, if you take a look at the contour integral over c, so this whole entire contour I've just called it c, we can obviously decompose this into the separate parts. So the integral over well, I guess gamma minus I infinity to gamma plus I infinity, and then we also add the integral over this gamma. But we also know by the residue theorem that this contour integral is equal to 2 pi I times the sum of the residues of the function or the integrands in here. And if we can show that the integral over gamma in the limit approaches 0, so let's say this goes to 0, then in fact what happens is that instead of evaluating this integral, which is pretty nasty, all we have to do is just calculate the sum of the residues of our function, which is a lot nicer to do. So that's why it's really nice when our integral over this big gamma over here goes to 0 in the limit. And that's what we're going to be proving in this video. I'm going to be proving in this video because we are going to be using it for later videos, and I don't want to prove the same thing over and over again. So let's go ahead and show that this is true. So first of all, I'll need to impose some kinds of restrictions on our f of s. It can't just be any function, otherwise this wouldn't really work. So we have the requirement, that's our f of s is expressible as the quotient of two polynomials. So let's call it p of s and q of s. So p and q are some kinds of polynomials. And what we need from these two polynomials is that the degree of, for example, q minus the degree of our p is greater than or equal to 1. So let's say, for example, the degree of P is 2. That means the smallest the degree of Q can be is 3. So Q can have a degree of 3, 4, 5, 6, but it can't have a degree of 2 because otherwise this inequality wouldn't hold. Alright, so let's plug this into our integral. We're actually not going to worry about this limit. We're going to be taking the limit at the very end. And also, since we want to show that this goes to 0, it's nice if we can find some kind of upper bound for this integral. So let's estimate it. So let's take the absolute value of the integral over gamma. And this is equal to the absolute value of the integral over gamma of P of s divided by Q of s times e to the st ds. Alright, and from here what I want to do is I want to start parameterizing things a little bit. Notice that the s's on this curve gamma is basically part of a circle. So what we can do is we can rewrite s as being r times e to the I theta. Because notice it's on a circle of radius I, and this angle theta sweeps around this circle. And we can figure out what ds is equal to. That's equal to I times r e to the I theta, d theta, so just some chain rule over there. And what we have to figure out now is what exactly are our values of theta, because that actually depends on this gamma. So what we can do now, notice that we can construct a nice right angle triangle over here. This alpha that I've labeled, we can actually rewrite that in terms of r and gamma, because notice what this length over here, that's a gamma as well. So notice that the sine of alpha, because this is opposite and hypotenuse, sine of alpha is exactly gamma divided by r. And I'm just going to leave this angle as alpha because I don't want to write sine inverse of gamma over r all the time. But in particular, our angle, our theta over here, it actually starts at pi over 2 radians minus alpha. So theta is going to range from pi over 2 minus this angle alpha that I've labeled, and we're going to make it run all the way up until, well, we have 3 pi over 2 on over here, and by symmetry we're going to add on an alpha. So we're going to go to 3 pi divided by 2, and then we're going to add on an alpha here. So that's the interval we're going to be integrating across once we substitute into our theta variable. So now let's rewrite this integral. This is now equal to the absolute value of the integral over, well, this interval now. So that's pi over 2 minus alpha, 3 pi over 2 plus alpha. And I'm going to leave this P of s and Q of s as it is, just because I don't want to make anything messy. We're going to deal with that later. So P over Q, and then we have E, and then S is going to turn into R times e to the I theta, and then we're going to multiply by t. I'll just put it there. And our ds turns into I times r e to the I theta d theta. Then we're going to end off the absolute value. Alright, now since we're integrating with respect to a real variable, we can use the integral inequality to say that this is less than or equal to the integral, and then we're going to put the inequality on the inside. So first of all, we're going to have the integral from pi over 2 minus alpha to 3 pi over 2 plus alpha, and then we're going to have our P of s divided by Q of s, and we're going to have absolute values around these as well. And then we're going to take the absolute value of e to the t r e to the I theta, and then we're going to take absolute values everywhere. So absolute value of I is just 1. Absolute value of r, well, r is positive and it's very big, so it's going to jump out here. It's just a constant. And absolute value of e to the I theta, well, that's just 1. And then let's end it off with a d theta. Alright, so we've made a mess over here. We have absolute values everywhere. What I want to focus on now is the absolute value of the quotients of these two polynomials, because in fact we can find a bounds for this. So let's take a look at the P of s, and since this is a polynomial, we can write this in the form an times s to the n plus dot dot dot, and then all the way down to a0 s0, and we can do the same thing for q as well. So we have q of s, and that's equal to, let's say, b sub m. So these powers are going to be different. So we're going to have s to the m plus a dot 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 plus B0, S0. And we're taking the quotient of this, obviously, so let's just divide everything through over here. So these are equal, and we're taking the absolute value of this. So let's take the absolute value everywhere here as well. All right, and what I want to do now is I want to take a look at the behavior of S. And notice S, well, that's just all the points on this circle. And notice it has a radius of r, or the modulus is r, and r is going to be very, very, very big. So in fact, what's going to happen is that the magnitude of all these complex numbers as over here, they're going to be very, very, very big. And since this is a polynomial, these are both polynomials, the only parts that really matter as s gets really big is just the leading terms over here. So in fact, what happens is that everything after the leading terms become irrelevant, so we don't really have to worry about that because the dominant terms are just going to be these leading terms. And you can use, for example, the triangle inequality up here and the reverse triangle inequality on the denominator to kind of bring the absolute values onto each term. So we can say this is, I guess, less than or equal to, because if you use the triangle inequality on the top, this is going to be less than or equal to something. If you use the reverse triangle inequality on the bottom, it's going to be greater than, but since you're taking reciprocals, it's going to be less than. You can probably try it out for yourself and you should probably get the same thing that I'm getting, but you should be able to write it as the absolute value of a sub n and then s to the n. And then you have a bunch of absolute value junk on the end as well that we don't really care about. And also this is divided through by b to the m, s to the m, plus a bunch of other junk that we don't really care about. Remember that s, the radius or the modulus of s, is getting really big. So these dominant terms are going to be what really matters. So we can say this is asymptotically equal to the absolute value of an and then absolute value of s to the n over the absolute value of b sub m and then absolute value of s to the m. And we don't really care about the other stuff because they're not going to contribute not much as our modulus of s gets really big. And notice the modulus of s, well, that's just the distance of all the complex numbers on this circle away from the origin, but that's exactly the radius r over here. So in fact, this becomes these two coefficients. We can just simplify that down to some random coefficient, c, for example, and we're going to have r to the m divided by r to the m. And notice n and m are actually the respective degrees of the polynomials p and q. So since we have this inequality over here, the degree of q minus the degree of p is greater than or equal to 1, we can do something similar down here because the degree of q is exactly m, the degree of p is exactly n, and this is greater than or equal to 1. Well, if you look at this fraction over here, we can say this is c times r to the n minus m. Well, n minus m, well, that's just going to be, let's see, it's going to be less than or equal to negative 1. So this is less than or equal to c times r to the minus 1, or we can just say this is c over r. So what did we just find over here? We found that in the limit, as our r approaches infinity, as r gets really, really, really big, this quotient of two polynomials is actually bounded above by c over r, where c is some constant that we can pick that's, I guess, big enough to be a bound. So we can actually substitute this into our integral over here, because this part over here, it's less than or equal to c over r, so we can find a new upper bound for our integral. So let's erase all of this, and now we can say that this integral is less than or equal to r times the integral from pi over 2 minus alpha to 3 pi over 2 plus alpha of c divided by r absolute value. And now I'm going to do some expansions on this exponential function here. Notice we can use Euler's formula for e to the I theta, and we're going to get e to the t times r. Well, the first part of Euler's formula, that's cosine of theta. And then the second part, well, we still have the t times r. We also have an I out here, and it's going to be sine of theta. And obviously we integrate this with respect to theta. Alright, and notice now these r's over here and here can cancel out, which is quite nice. And the c obviously can jump out to the front. So now we have c times the integral from pi on 2 minus alpha to 3 pi on 2 plus alpha. And then we're going to get the absolute value of this stuff. But notice we can split the exponential function up a little bit using some exponential properties like so. And also we can split the inequality, or not the inequality, yet the absolute value across this product. So we get the absolute value of both products like so. And notice over here, t is a real number, r is a real number, sine of theta, since theta is on a real interval, it's also real. So all of this stuff over here, it's real. And whenever you have the absolute value of e to the I times some real number, that's just 1. So this thing can disappear. And over here we have e to the t times r times cosine of theta. All this stuff up in the exponent is real. So no imaginary stuff going on. And the exponential function is always positive for the real numbers, so we can ignore the absolute values. So this is e to the t times r times the cosine of theta times d theta. Alright, it's very nice. So we've come quite far so far. We've found a new upper bound for our initial integral that we started off with. Let's just erase all of this stuff that we don't really need anymore. So we just found that the absolute value of the integral over gamma is less than or equal to this thing that we found. So that's c times the integral from pi over 2 minus alpha to 3 pi over 2 plus alpha e to the t times r times the cosine of theta and d theta. And now we're going to be doing quite a bit of graphing actually. So this is where the high school maths come in. So first of all, what I want to take a look at is this cosine function. So if we draw up the cosine graph, it's going to look something like this. So over here, this is pi on 2. We have 3 pi on 2 here. Obviously this midpoint over here is pi. And what is the interval we're integrating across? Well, we're going from pi on 2 minus alpha. So it's pi on 2 and then we subtract off a little bit over here. So this point over here is pi over 2 minus alpha. And then we're going up to 3 pi on 2 plus alpha. So that's 3 pi on 2 plus a little bit over here. So this thing is 3 pi over 2 plus alpha. So we're integrating on this whole entire interval that we have. And my goal is to kind of rewrite the bounds a little bit nicer, I guess, because I kind of want to shift this back to near the origin. It's a little bit easier to work with that way. Notice that if we instead took a look at so this is the graph of cosine of theta. If we take a look at the graph of minus cosine of theta, it's going to look like this. And I want you to notice one thing. The values that we're getting out of this cosine of theta on that interval are the exact same values that we get if we just go from 0, so this is 0, to pi on 2. And then we add on a little bit of an alpha. So this is pi on 2 plus alpha. So consider this interval now from 0 up to pi on 2 plus alpha. Notice that the values we get out of the cosine function, well, that's just half of the values that we get from here, but we can use a bit of symmetry on the integral to, I guess, double it. So this integral, we can in fact rewrite it as this the integral from 0 to pi on 2 plus alpha, but then we just multiply everything by 2 because, well, because the cosine function is even. And hopefully you guys can see this because the values of cosine that we get on this new interval over here are the exact same values that we get on the cosine of theta graph on this interval, but we're just going to double it because of symmetry. So this integral, we can rewrite it as follows. This is equal to the, well, we have c times the integral. Now we're going from 0 to pi on 2 plus alpha instead. And then we're going to have the same integrand, so e to the t times r times the cosine of theta d theta. And obviously this only gives us half of the integral, and to get the other half, because it's symmetric, we can just multiply the whole integral by 2. Alright, so this is what we have right now, and in fact this should have been a negative because we drew a negative cosine graph this was a negative cos graph. So here we had to replace cosine with negative cosine. So that's quite important. We need e to the minus tr cosine of theta. And now what I want to do is I want to start finding a new upper bound for this integral because, well, this integral is very hard to evaluate. We've never integrated something like e to the cosine of theta. That's very hard. Since we're just finding upper bounds of this, we can kind of approximate cosine with some kinds of linear function, which is a lot easier to integrate. So let's investigate this a little bit. First of all, let's take a look at the exponential function. Notice that this is a decaying exponential, so we have e to the minus something. T times r, those are just constants in terms of theta, so we don't really need to worry about that. So if you just call, I guess, this whole entire thing x, if we take a look at the graph of e to the minus x, like so, notice that if we pick some value, let's say a over here and b over here, then e to the minus a, if we plug in, actually we'll just do b, if we have e to the minus b, so we're getting the output over here, notice that it's less than or equal to e to the minus a, so plugging the a into the function, if and only if a is less than or equal to b. So how does this actually help us? What this is saying is that in order to find a new upper bound for our function over here, we need to find a function in the exponent that's less than or equal to what we currently have. So imagine this whole entire exponent, that's kind of like our b at the moment. In order to find a new upper bound for this integrand, we need to look for some kind of a, because if we can find an a that's less than b, so if we can find a function that's less than or equal to the function that we have in the exponent, then in fact we find a new upper bound for our entire exponential function. So our goal is now to find this particular a, which is always less than or equal to b, which is what we have currently. So in order to do so, we're just going to ignore the t times r because those are just constants. I want to look at the cosine graph once again. So if we take a look at the cosine graph on this interval, so we're going from 0, and then this over here, that's pi over 2, and then we're taking pi over 2 plus alpha, so maybe that lands us somewhere down here. So this is pi over 2 plus alpha. We want to think of some kind of function that's always less than or equal to this cosine graph, and a nice function that is always less than or equal to this cosine graph is a straight line that joins this point to this point over here. So I guess I'll do this in red just to make it a little bit more clear. So we're looking at this line over here. And in fact, I've drawn this line so it's always less than or equal to the cosine graph. But if you have a keen eye, you might notice that this is a little bit deceptive, because imagine if our alpha was a little bit bigger. So we have the same cosine graph over here, but let's say our alpha was a little bit bigger, so obviously this is pi over 2 over here. If alpha was a lot bigger, let's say over here, so pi and 2 plus alpha, and we look at this point over here, then if you make the same line from this point, which is 0, 1, down to the point down there, then in fact it's not always less than or equal to it. There's part of it that's above the cosine graph, which is not quite what we want, but the good thing is alpha will always be small enough such that this happens, because remember, r is getting really big, and we had that relation, I think I rubbed it out, but the sine of alpha is equal to gamma divided by r. So if you take sine inverse on both sides, alpha is sine inverse of gamma divided by r, and we want r to be really big, so the argument inside of the sine inverse function will be quite small, which means alpha will be a small angle as well. So as long as the r is sufficiently big, then we can find some kind of alpha that's small enough such that when we construct this red line, it's always going to lie below the cosine graph. Alright, very nice. So now we just have to find out what this line is equal to. Well, we already know what this point is. It's 0, 1. That's quite easy. And how about this point down here? Well, we know the x-coordinate, or the theta coordinate, I guess, is pi over 2 plus alpha, comma, the y-coordinate. But what is the y-coordinate? Well, that's pretty easy. Let's just sub pi over 2 plus alpha into the cosine function. Let's find cosine of pi over 2 plus alpha. If we evaluate this, then we're going to get, using the angular sum identity for the cosine, that's cosine of pi over 2, cosine of alpha, and minus sine of pi over 2, and sine of alpha. But notice cosine of pi over 2, that's 0, which just kills off this whole entire first term. Sine of pi over 2, that's exactly 1, which is quite nice. And we know sine of alpha, that's exactly gamma over r. So in fact, this thing evaluates to minus gamma divided by r. So that is in fact the y-coordinate of our red line, so minus gamma divided by r. And now, since we have 2 points, we can figure out the equation of that line. So in order to find the equation of the line, let's first, I guess, find the gradient. So gradient is a rise over run. So rise over here, that's 1 minus negative gamma over r, which is just 1 plus gamma divided by r. So that's our rise. And for our run, it's 0 minus pi on 2 plus alpha. So I'll chuck the minus out here, and then we'll have a pi on 2 plus alpha out here. So this is our gradient. We multiply it by a variable, which is in this case theta, and then we also have to add the y-intercept, which is 1, so we'll just slap a 1 out here. So I guess y is equal to 1 minus this thing times theta. That's our red line. And let's just clean things up a little bit over here, because this is looking a little bit messy. Let's first of all multiply the top and the bottom of this fraction by r. So multiplying the bottom by r, we're going to get a denominator of r out here. And multiplying the top by r, we're going to get r plus gamma. And then multiplying the denominator and the top again by 2. In order to get rid of this 2 down here, we're going to get a pi plus 2 alpha. So that's multiplying the denominator by 2, multiplying the numerator by 2, we're going to get a 2. And obviously, let's put this in parentheses, and let's put a theta there. So what can we say right now? We can say that for all theta on this interval, so that's the interval 0, pi on 2 plus alpha, since this function is always less than or equal to this cosine graph, we can use that inequality that we had earlier. So when we take the decaying exponential on both sides, what we actually find is that e to the minus t times r times the cosine of theta is less than or equal to. Now we're just going to replace cosine of theta with what we found over here. So that's e to the minus t times r. And then we're going to multiply this by this function, but let's multiply by this one first. Let's might as well distribute everything. So multiplying by 1, we just get, well, e to the minus tr. And then multiplying by the second part, we're going to get another exponential function using some exponential properties. Well, notice minus and minus will cancel out, leaving us with a positive. R and R will cancel each other out, leaving us with just 2t. And then we're going to get this part over here, I believe. So that's r plus the gamma divided by pi plus 2 alpha times theta. And this is for big R. So if R is sufficiently big, then this inequality will hold. So we've just found a new upper bound for our current integrand, which is what we had. Let's plug that in. And our integral will actually be a lot easier to evaluate, which is quite nice. So now this is less than or equal to 2c times the integral from 0 to pi on 2 plus alpha of, now we're going to have e to the minus tr, so that's the first part over here, and then we also get e to the 2t r plus gamma divided by pi plus 2 alpha times theta d theta. And obviously this is a constant over here, so that can jump out to the front. But notice this integrand that we currently have, that's quite easy to evaluate, even though it looks like a complete mess, but it's just the standard exponential function. So let's go ahead and evaluate that. That's going to be equal to 2c, and we're going to bring this constant out to the front, so that's 2c e to the minus t times r. And in order to find an antiderivative for this, well, notice this is e to some kind of linear function of theta. So we're just going to take the reciprocal of this outside factor. So that's going to be 1 over 2 times t, and then pi plus 2 alpha divided by r plus gamma. And then we're going to multiply by this function because the antiderivative of an exponential is still an exponential. So we're going to get e to the 2t r plus gamma divided by pi plus 2 alpha times theta, and evaluate this from 0 to pi on 2 plus alpha. And obviously some nice simplifications can occur. This 2 and 2 can cancel, for instance. And what are we left with? We're going to have now c times e to the minus t times r divided by t. And then we have this parentheses over here, so that's pi plus 2 alpha divided by r plus gamma. And we're going to multiply this. Well, we're just going to sub each of these endpoints into this function. So that's going to be a little bit messy, but should be alright. That's e to the 2t r plus gamma divided by pi plus 2 alpha times our theta, but we're plugging this upper bound in, so that's pi over 2 plus alpha, and then plugging 0 into here. Well, that's just going to kill the whole exponent, leaving us with just a minus 1 like so. Alright, so basically what we've done, we've gotten rid of the integration. This is our new upper bounds for our original integral over gamma that we started off with. So this is looking very messy, but we can actually show that this goes to 0 in the limit as our r approaches infinity. First of all, let's take a look at these alphas, because remember, alpha is exactly inverse sine of gamma divided by r. And since r is on the denominator, when r gets really, really big, then the argument of the inverse sine goes to 0, which means that when we take the limits as r approaches infinity on our alpha, it actually goes to 0. So right away, taking the limit on this thing, so we're just going to take the limit bit by bit. So taking the limit as our r approaches infinity, this is going to be equal to, well, we have the limit as our r approaches infinity again, of c times e to the minus tr. I'm going to leave these r's as they are. We're going to deal with them later. And then we're going to have, well, alpha is going to turn into 0. So that's going to be pi divided by r plus gamma. And then we're going to have e to the 2t and then r plus gamma. So r plus gamma divided by just pi, because this alpha is going to turn into 0. And then we have pi on 2 plus alpha. Since alpha is going to 0, we can just write pi divided by 2 minus 1. And of course we can do some simplification. These 2's will cancel out, these pi's will cancel out. And what are we left with? We're left with the limit as our r approaches infinity of c times e to the minus tr divided by t pi over r plus gamma. And you might see that we have a decaying exponential over here, so that obviously goes to 0, but we have to make sure that everything on the right is finite. Unfortunately though, we do have e to the t times r and e to the t times gamma. That's what you get when you expand out here, minus 1. So we have a e to the tr, which is being a little bit problematic. But the nice thing is, if we expand everything out once again, it's actually going to cancel out with what we have here. Let's actually make things a little bit simpler by taking this c, this t, and this pi out to the front. So this is going to give us pi times c divided by t. The limit as r approaches infinity, we still have this 1 over r plus the gamma guy hanging out the front. And then if we distribute this e to the minus tr into each of these terms in these parentheses, we're going to get, well, first of all, it's going to cancel out with this e to the tr, which is good. We're getting rid of that problematic thing. So that's going to give us e to the t gamma, which is the thing that remains. And then distributing this e to the minus tr into this negative one, that's negative e to the minus tr. And now, obviously, you can see that taking the limit as r approaches infinity over here, this is going to go to 0. So this is going to be some finite value, and since r is on the denominator here, as that approaches infinity, this whole thing goes to 0. So overall, since pi, c, and t are also finite, this is going to go to 0. So we get an answer of 0. So what did we just find? We've just shown that if we take the limit as r approaches infinity over the integral over gamma, like so. This is going to be less than or equal to the limit of the upper bound, which just evaluates to 0. So since the limit of the absolute value goes to 0 and the absolute value is positive, this can only mean that when we take the limit as r approaches infinity on the integral over gamma, that's going to give us 0, which is exactly the lemma which I wanted to prove today. So that was quite a long video. There's quite a bit of steps involved. Since I've gotten this video out of the way, now that I make further videos on the Bromwich contour that involves the calculation of the integral over gamma, I don't have to go through all of this again because it does take a while to prove this. So yeah, with this result, as I said before, the inverse Laplace transform formula does become quite easy to evaluate. It just becomes a problem of evaluating those residues, given that our f of s is expressible as a quotient of two polynomials p and q, where the degree of p is less than the degree of q. So that's pretty much all I have for this video. Hopefully you guys enjoyed it. If you did make it to the end, well, thank you for watching the whole video. I appreciate it. And until next time, I hope you guys have a wonderful day, and I'll see everyone later. Bye bye.